Brett Finney is from UC Davis, and I imagine is well known for his large Twitter following, probably best known for that. But yes, he's runs a core facility at UC Davis. I think one of the more well-known and one of the few profitable core facilities.
As of yet, we'll see. All right, hi everybody. Well, thank you very much for inviting me. I'm excited to talk about some of the DIA work we've been doing over the last year or so. And I'm glad to be here. And I'm, like Sue said earlier, DIA has been really exciting, and I'm really excited about it. You can probably tell when I talk about it. So I'm going to have a lot of slides. I'm going to race through some of them and spend a lot of time on others. And I kind of wanted to get the perspective of using DIA in an academic core facility, how we optimize them, some trade-offs we've made in order to make things cost-effective to some of our clients. So as I said, I'm at the UC Davis Proteomics core facility. We're part of the UC Davis Genome Center. They have other cores like genomics and metabolomics, and we have proteomics. UC Davis is pretty unique, and I'll touch on this in some of my DIA talks, as it'll make a little difference, is that there's a lot of agriculture and there's a lot of medical research. So we do like a fair amount of human work, but we also do maybe 60 to 70% of our work is weird agricultural products like grape sap and Xylella and all sorts of corn and all sorts of things, melons. But probably 30% of the 40% of the stuff we do is human, and 60 to 70% is other stuff. So we run a lot of different kinds of samples, which is going to be a little important for DIA. Why did that not work? Okay. All right. So this is what our collaborators and they used to be customers, right? But proteomics has changed in the last 5 years, where it used to be a lot more service work where people could bring you stuff and they'll say, hey, we want to identify what proteins are in here, and you chop up a gel piece or you do an in-solution digestion. You say, hey, here's what proteins are in there, and that's pretty much all you could do. These days, that's kind of dead or dying, right? Like, nobody really cares what's in there very much anymore. It's all kind of, how much is in there, right? So most people are interested in quantitative proteomics profiling or PTM identification, and not only PTM identification, but quantitative profiling across post-translational modifications. And I've been telling people for a while that no one really comes to me anymore and says, I want to know what proteins are in there. It's usually, even if they do, they really want to know how it's changing, even if you do like an affinity purification or something. It's not just what's in there, but how things are changing. We also want things to turn around quickly. It's kind of hard to do science when things take 2 months, and then it doesn't work, and you have to do another 2 months, and then they give up and go away, and you don't blame them. So before Scaffold DA, how I used to do stuff is we would do the profiling, quantitative profiling by DDA, which is what most people do, right? And we would either do spectral accounting or label-free quantitation. And when I say LFQ, that's the traditional MS1 LFQ, right? Or we'll do TMT, either 10 plexes or 11 plexes. This is kind of hard to read, but here's just some data from a paper we published like 3 days ago in Plant Cell using some older spectral accounting data. So, which is not surprising, because spectral accounting can be pretty powerful if it's used correctly. And I was pretty excited about this data. It was actually kind of important. And what was nice about it is they held the paper because there's other proteomics people that discovered the same thing that used more sophisticated techniques, but we found it first with spectral accounting. So anyway, this is how we used to do things, and it's still used, right? Like, I think this data is a year old or so, but the paper was just published this a couple days ago. Okay, so this is how we used to do it. And some of the problems we have with MS1 LFQ is data-dependent stuff is, this is kind of what our chromatograms look like. They're okay, they're not great. And if this is kind of a typical Orbitrap MS spectra, right? You see tons of peptides coming out all at once. If you zoom in, most of these are actually peptides and not background atoms. Some of them have really nice signal to noise, right? So like when you look at the isotopes of this peptide, this is actually a +4, I just picked it at random, and you plot the XIC, you get a really good signal to noise, and so if you're doing an MS1 LFQ, you can kind of get a nice quantitation of that. It's not so hard. But if you actually go in and look at Orbitrap data down in the grass, right? Like right here, this is kind of what it looks like. And so here's like a M over Z 540 to 570. There's probably like 50 peptides in there, right? And so you can kind of zoom in, and when you start plotting those in the MS1 level space, it gets a little noisy, right? It gets a lot noisy, actually. And so you can do some sophisticated things like this is from MaxQuant. There's a peptide, random peptide I'm going to be showing you over the next couple slides. And you can kind of see that here, and it does an okay job, right? Like it picks it out, but you can see how complicated this data is, right? So one of the main problems I've always had with MS1 LFQ is the missing values. And this is underappreciated by some people, but you see it mentioned more and more. Like a couple people at Thermo's talk this morning mentioned it. And these are actually really good levels for MSQs for my data sets. And you could get between, out of three replicates, you could get between 16 and 23% of your data being missing, right? And that's an awful lot. And I've seen this up to like 30 or 40% sometimes. And I'm not really sure what it depends on, more of chromatography or sensitivity. It's probably a big combination of both. I suspect it's a signal to noise issue. But this is even with match between runs turned on, and we're getting missing values in MaxQuant between 16 and 23%. So it can be quite significant, but it still works okay. So that was before we got Scaffold DIA. And I didn't really wrap my head around how this was different. So like several years ago, I tried DIA Empire, and I really didn't like it. With the wide windows, it didn't work really well for me. And that kind of turned me off to DIA for a while. And then it took me a long time to figure out what peptide-centric DIA means. And there's a lot of different ways to do DIA. And it took me, I think I only really started, I don't even know if I completely understand it. But it took a long time for me to wrap my head around what peptide-centric DIA actually means. But before Scaffold DIA, the DIA software was difficult to use. I still don't know how to use OpenSWAT. The outputs were usually tables of TSV or CSV values that you have to put in Excel and sort or R. There's no visualization. One of the things that was really difficult for me with data-independent analysis, it seems like there's a million different ways to do things, right? There's like 1,000 ways to acquire your data. What window size do you use? Do you stagger or overlap them? Do you use the libraries? What libraries do you use? Do you use DDA libraries, DIA libraries, a combination of lots of them? It was really hard for me to really understand. And then once you get through how to acquire the data, there's like lots of different ways to analyze the data, right? Especially with Scaffold DIA, there's still a lot of ways to analyze the data, right? What libraries do you use? Do you use FASTA? Do you make your own chromatogram libraries? It can be really challenging, and it was challenging for me for a long time. So peptide-centric DIA, I'm not really going to go through too much, but there's two papers I think that really helped me. There's the PPAM paper, I believe this is taken in 2015. That's a really good paper that kind of helps you understand what Scaffold DIA is doing, especially if you're searching FASTA files. And then there's Brian's encyclopedia paper that came out in Nature Communications, right, 2018. And if you read those two, it kind of goes through. After reading this, I kind of got a better idea of how Scaffold DIA is doing things. You kind of get a picture of these nice little plots. And there's a little tools menu in Scaffold DIA that you can actually reproduce some of this stuff, and it's nice. So here's an example of a random peptide from a data set I'm going to show you later that was kind of identified by and quantified by Scaffold DIA. Here's the precursor, doesn't really use this. But here's the Y and EI, and says they line up over time. You can kind of see how they all line up. And it looks kind of nice looking data. Let's see here. And then here's this slide's kind of out of place, sorry. This is one of the first slides when I looked at, this is kind of a replicate, a scatter plot of DDA data that I put in the Scaffold. And here's the exact same one with Scaffold DIA. I ran the data set twice. And you can see there's a clear set of proteins that are being downregulated in with this sample versus this sample. And you can't get that at all with DDA. And these all made sense biologically. And I looked at that and I was like, whoa, this is way better. And I'm like, okay, screw this. I'm going to start doing more DIA. And then so that's what I started doing. So we also do DIA we also do a lot of TMT in the core facility. There's some advantages or disadvantages versus them. DIA there's no labeling, so it's faster. You need a smaller amount of total protein required compared to TMT where you need more. DIA can actually be more expensive than TMT. How is that the case? Well, TMT can't be cheaper. The DIA missing values are higher. Data analysis is easier for less than 10 samples, way easier for less than 10 samples. TMT data analysis is easy for less than 10 samples. For greater than 10 samples, DIA data analysis is easy. TMT requires more proteins, can be cheaper. It really can be cheaper because of the multiplexing. So even if you pay for the labels, if you multiplex and not fractionate, TMT can be a lot cheaper. TMT, the missing values are really low, like way lower than either DIA or DEA. But data analysis for spanning more than a 10-plex is complicated. So talk to Phil back there. It's actually, I found it very complicated, but it can be done really accurately. So here's some DIA methods that we've been using, recommended by Brian. And I'm going to go into this and give you kind of a method that we kind of came up with somehow. So these are some of the methods that I used in the data set I'm going to present that Brian gave us. We used a combination of a narrow window library and a wide window acquisition. So usually for the narrow window chromatogram libraries, you're stepping at 100 Daltons at a time, 60,000 resolution, root count of 25. You guys can all go through this later, but basically what it is we're going through a narrow chromatogram library window. And I'll give everybody this, it's not a secret. And then we're doing a wide window acquisition for the actual experiments. And then here's the MS settings. So the problem with this method, by the way, is that in a core facility, if you run 2 samples, a lot of times I was like, well, I'm not going to run 6 chromatogram. I'm not going to make a chromatogram library with 6 runs for 2 samples. That doesn't make any sense. And then actually run 2 more, so 8 runs total for 2 samples, or 2 or 3 samples. So I was like, that's not going to work. That's going to be too expensive. And then, so somehow we came up with this method. I don't know who came up with this method. It might have been Tony in the core. I don't know where it came from. Nobody can quite figure it out. But what we ended up doing is using a 2x gas phase fractionation method, a narrow window method. So instead of running six chromatogram library windows, we run 2. So it's a window size of 4 Daltons, and we basically go from 360 to 758 in one run, and then 760 to 1150 in another. I don't know why we go 2 Daltons in this. And so each run is about 100 windows. We times that by 2, so 200 total. They're not staggered, and then here's the collision energy, the max inject time, and the resolution, and the AGC target. And these could probably use some optimization, but that's kind of what we're doing. And I honestly forgot where this method came from. I don't think I made it, but somehow it appeared in the lab. So this is an example of data acquisition for, like, if you use a wide window method versus our 2x gas phase fractionation. So like the wide window, you would use an 8 Dalton window size, 8 to 12, and you would go between 400 to 1,000, about 151 windows. You would stagger them so they would be half overlapping, so they would be convolute. Here's the collision energy. You see the AGC target's a little weird, and that's only weird because we wanted to maximize the 20-second. We want it to be 20 milliseconds every single time. And then this is kind of comparing to the method I'm going to show you, which is the 2x gas phase fractionation. So those are kind of the differences. So the 2x gas phase fractionation is similar to a chromatogram library, except we're only doing two fractions instead of 6, or we're doing 2 runs instead of 6. So we're doing 6 here, 4 same Dalton window. They're not staggered. 25 windows total, 60 milliseconds. ADC is set high again. So here's why we wanted to do this in a core facility, because here's kind of the number of samples that you want to analyze, the number of runs needed to acquire them. And so this is versus the gas phase fraction, the 2x gas phase fractionated method, versus the chromatogram library and the wide window, so the narrow chromatogram library and the wide window acquisition. And you can see they scale differently, right? And so it kind of works until you get to 6. And then once you have 6 samples, they're the same. And then once you have more than 6 samples, it gets more efficient to do the chromatogram library and the wide window, because you make the chromatogram library once, and then you do 1 acquisition per sample instead of 2 acquisitions per sample over the entire time. And another limitation of doing the 2x gas phase fractionated sample is once you get to about 10, Scaffold crashes, so you can't do that anymore anyway. So I think it's like percolator crashes or something. You get too much memory and it just crashes. So anyway, I hope they fix that. I'll put that slide in here.
Write it on your little evaluation sheet.
Yeah. So I was talking to Brian about this method, and we were kind of going back and forth about it. And we were like, well, Brian was like, oh, you should check the number of scans across the peak, because Brian made this really nice graph about how scans across the peak are really important, right? And I'm like, oh, I should do that. So I had to do this manually, and that's one of my wish lists for Scaffold DIAs, that they would calculate the number of scans across the peak you're getting. But so I did it, I actually opened the raw file and counted by hand how many cycles every time I saw a certain window, and wrote down the retention time and calculated it myself. So if you have the 2x gas phase fractionated sample, you get about 16 scans over 2 minutes. So that's 8 cycles per minute. I guess it's not great, that's okay. The 8 Dalton wide window, which you would think you would have a lot of scans across the peak. So you actually have, this is the 8 Dalton wide window staggered method, where you have 8 windows, but you stagger it twice. And so that's actually 19 scans at 2 minutes, or 9.8 scans across the peak. Now, how it's deconvoluted, I have no idea. Brian could tell you. I don't know the math about how many scans. So I counted it manually, but when you deconvolute it, then how many scans across the peak you get, I don't have any idea. So I don't know if that number's right. But then I went and looked at Scaffold DIA, and here's the wide window, the 8 Dalton staggered one. And I think I just kind of counted. I don't know if this is accurate. I counted when there's an angle. And I think there's about 6 scans across this peak. This is just a random peak from my experiment. And the 4 Dalton 2x gas phase fractionated, I got like 7 total. I don't know. They look kind of similar if you look at them. So I don't see one being slightly better than the other. I don't know. Maybe they're the same, or maybe one's better than the other. But I tried to do it by hand because I didn't have any other way to do it. The only other way to, when you put data in Scaffold DIAs, you have to kind of organize it a little different. This took me a while to figure out, because when you have two injections per run in an experimental data, half your data is going to be missing by default, right? Because you're going to find a peptide in one window, and then the other one is going to be missing because it's not the same mass, right? It's going to be outside the window. So you want those, you don't want those averaged, or you don't, because you don't want a zero average with your experimental value. Okay. So the method we use in the lab, the 2x 4 Dalton window, it seems to work. I mean, I think that's the biggest advantage I see. I run real data sets through it, and it seems to work. It's good for between 2 to 5 samples, so it's good in a core facility where someone gives you 2 samples, or you want to do a pilot project and you just want to run it and see what your DIA data is going to look like. It's going to look nice. The quantitation seems decent. Scans across the peak, I guess, seems decent. The cons is it requires more runs per sample, right? So you need to do 2 runs per each sample. And then Scaffold percolator is actually one that crashes. But it will crash after like 10 samples, and I'm not exactly sure why. I think that may be only when you're searching with a FASTA, but I'm not entirely sure why, but it does crash. So here's an example experiment we did a couple weeks ago. It was a human profiling experiment. Had about 5 different conditions and 3 biological replicates per condition. So not a huge experiment, but not a small one either. So we used I actually ran this 3 different ways, because I was kind of, I'll show you why I ran it 3 different ways. But I ran it once with the chromatogram library and the 8 Dalton window, and ran it again with a subset of it with the 2x gas phase fractionation. And I also ran it through DDA, so we're going to compare all of them. And it's kind of cool to look at the data. Oops, that's not good. How did I? Okay. And then here's my chromatogram library. I'm going to rush through this, but you can look at the talk later, and I'll give it to you or whatever. Here's the kind of the conditions we use. Okay, so the experiment, when we do PCA, as we talked about this, the PCA and the heat map are really useful. When we look at it, it seemed to work. These are 2 of the conditions that are clearly separated. These 3 are clustering together, and biologically, this is what we expect from this experiment. So it seemed to work okay. There's several proteins in here. This is a knockdown experiment. There's several proteins that are known to be knocked down. This is one of them. And we know they're knocked down in these 2 conditions, and they are. That's good. So it seemed to work. Here's another protein that was known to be knocked down in these 2 conditions, and they are knocked down. So that's good. It seemed to work. I'm surprised it didn't work. Okay, so when I searched this method through Scaffold DIA, I originally, here's the FDR settings I use. These are all default. Scaffold, so it requires 2 peptides per protein, 1% FDR. And I only quantified about 2,373 proteins. And I'm like, oh, this sucks. You know what happened? That's not very good. You know, Sue told me I should be getting like 6,000 proteins. And I happened to be talking to Sue on the phone that day. And it's always good to talk to Sue because good things happen sometimes. And she's like, oh no, you're doing this wrong. Because what I did was I made the chromatogram library with the FASTA for human, and that's what I did, and I got 2,300 proteins. She said, no, you need to be making your chromatogram library with the PanHuman library. I'm like, oh, you can do that? I didn't even know you could do that. And then of course I read Brian's Nature Communications paper, and of course it's right there in the, in the encyclopedia paper, how you get your boost from that. And I was like, oh yeah. So then I redid it, and I made the chromatogram library with the PanHuman DLib, or the DDA spectral library, which Brian could give you. Or is that the only way you can get it, is from you, Brian, or is there other?
It's on the website. It's on the
our website.
Proteome software website.
Okay.
Yeah.
So anyway, Sue said, oh, you're doing it wrong, so I redid it, and the number of proteins quantified doubled. So it went from 2,300 proteins to 4,600 proteins. And I was like, whoa, I wasn't expecting that. That's huge. I was like, okay, that really worked better. That's really fascinating. And not only that, but the number of peptides doubled. Let's go back. More than doubled. It went from 15,000 to 46,000. I mean, that's a huge increase. And this is one of the problems I had with DIA, right? Is like, there's a million different ways to do it. And if you didn't do it, if I didn't talk to Sue on the phone, I would think the experiment failed because I didn't read Brian's paper carefully, or I didn't read the Scaffold manual that that's in there. I don't read manual. So anyway, so then I did a third search. I was like, well, this is fascinating. Maybe I could do some more permutations and see if this works. So I did a third one where I used the PanHuman DDA spectral library. And I didn't use the narrow chromatogram library at all. I just searched, because Sue said, oh, you could do that too. I said, oh, I'll do that. So I just searched the wide window 8 Daltons against the PanHuman DLib without making a chromatogram library. And I identified 3,236 proteins, so that was good. It's kind of right in the middle. Kind of what you'd expect, I guess. And so obviously I sent the best data out to the collaborator, and I asked her right before this talk, I was like, I'm giving a talk, how'd the data look? And she said, oh, the data looked great, and we're getting a lot of information from it, and it's probably enough for an entire PhD project. So this is why I get excited about DIA, is because I give data back to their collaborators, and they're like, holy crap, this is awesome. This is like, these proteins are validating, and this we didn't know about, and it's a very practical feedback I'm getting from the people that use that I give data to. And so I was really happy about that. Okay, so I decided to do for this talk, I decided to do some permutations of different ways to run Scaffold DIA. And so I compared both the 2x gas phase fractionation and the wide windows, and I'm going to zoom in on this here. So for the 2x gas phase fractionated method, I compared making a chromatogram library made with PanHuman, and that requires so first I took these, there's 5 conditions and 3 bioreplicates per condition, and I redid the experiments because I didn't want to do the whole experiment over, so I just picked 3 of the replicates for the bioreps for 1 condition. And so that's what these are. So if you're going to do the 2x gas phase fractionated method, you can make a chromatogram library with PanHuman. This requires 12 runs. So you do 2x of the gas phase and then a whole chromatogram library. And you may ask why you want to do that. I don't know exactly. And so you need 12 runs, and it takes about 18 hours. You can do it with the PanHuman library only, which means you don't make a chromatogram library at all. You just take your 2x gas phase fractionated and search it right against your PanHuman. That only requires 6 runs. I compared the chromatogram library made with the FASTA, right? So instead of searching it against the PanHuman, I searched it against a FASTA file. And then I compared the FASTA with no library, just searching it with the FASTA without a chromatogram library at all. And then I searched it against another library called Proteome Tools, which is from the Proteome disease site. Okay, and then I compared the wide window. So I used the wide window 8 Daltons. These are the 8 Daltons. And I did the chromatogram library made with the PanHuman. The wide window chromatogram library, but instead of making the chromatogram library made from the 6 fractions, I made it from 2. So I actually used the gas-phase fractionated runs to make the chromatogram library. But it seemed to work okay. I searched against the PanHuman only, the chromatogram library matings, the FASTA only, and then the whole Proteome tools again. And then I compared them all. Okay. So here's a comparison of the DIE methods for the 3 biorefs. That's why that number is going to be a little bit less than 4,600, because I didn't do the entire experiment over, I just did 3. So this is kind of hard to read, I'm sorry, this is as large as I can read it. So this is sorted by peptides. Yeah, this is sorted by peptides, I believe. So the top, this is sorted by peptides, so the method at the top, more peptides quantified to the least peptides. It turns out the 2x gas-phase fractionated method with the chromatogram library made with PanHuman identified the most peptides, followed by the 2x gas-phase fractionated PanHuman library only without a chromatogram library. They were virtually identical. And this kind of makes sense because this kind of is a chromatogram library, but it's only using 2 instead of the 6. So it was basically identical. But one required 12 runs and one required 6. Third on the list is the wide window, so the 8 Dalton with the chromatogram library made with PanHuman. This is about 15% less than the top one. So 38,000 peptides versus 45,000. And then the wide window chromatogram library with the gas phase fractionated made with the PanHuman. And so what's interesting about this is that the peptides dropped about 15% from 3,800 to 2,000 to 38,000 to 28,000, which is interesting. Proteins didn't drop very much, so I'll show you that in the next slide. And then the 2x gas phase chromatogram library made with the FASTA, right, as fourth on the list. And then the wide window, and you could go on and on and on, but the top performer was the 2x gas phase fractionated library that identified the most peptides. And then the bottom one was like 80% less, so that's a big change. That was the wide windows, Proteome tools, and the wide window FASTA. So like if you use Scaffold DIA and you just search a FASTA file without doing a library, you can get 80% less quantified peptides than you can with a library, right? And for me, that could be a problem because there's only like 2 libraries. There's human and there's yeast, and I don't know of any other ones publicly available besides the Proteome tools one. Anyway, we ended up making the Proteome tool spectral library ourselves because we couldn't find one with the retention times needed to make it. And anyway, you can read this later, but I actually ended up downloading the whole data set and researching about 375 files myself and made the library myself. I sent it to Brian, and then he fixed it, and then sent it back to me. So there's actually 2 libraries available now. So just a background, the Proteome tool is made from the synthetic peptides that cover about 80% of the human proteome. I'm not actually sure I made this library correctly. Some of it works. Okay, and then you can measure the depth. I only put this here because I think this would be a good feature that Scaffold DIA has, or Scaffold. If you go to Ron Beavis's website, proteomics.org, he has a bunch of tests you can use to monitor the depth of the human proteome, and he has a bunch of proteins you can look for, and these are all proteins involved with charging tRNAs, I think. And so he says if you find all these proteins, you can get a good coverage. You can make sure it's a good measure of your proteome coverage for human, right? And it actually works really well. So you can look for all of these proteins, and I plotted them all out in this experiment. We did find all of them. And some of these are really hard to find, so that way I know this experiment worked really well. So if you have a human sample and Scaffold DIA, I would suggest going here and looking at if you have these proteins, if it's a whole proteome. And if you do, if you're missing a big section of them, then your depth probably wasn't very high, or something was missing. And so if you have a good, according to Ron, you should have all of these proteins to have, or most of them have a good depth in your human samples. Okay, so what I also found interesting in the lab is I did a comparison. I took these 3 samples and ran them again with DDA on the same instrument. This was all acquired on a Fusion Lumos, by the way. And so this is a traditional top 20, I think, DDA or Fusion Lumos. And then I wanted to look at the comparison of DIA versus DDA, because I used to do a lot of DDA in the lab. We still do, but I'm trying to move everything over to DIA. And I sorted by the method that worked the best. worst, and I compared it against MaxQuant. So I wanted to compare it against, I don't think MaxQuant's the most sensitive search algorithm in the world, but I wanted to compare it with something that a lot of my students use and a lot of people in the, it's easy to use and it's kind of hard to screw up. And a lot of our collaborators use it because it's free and it works okay. And it's basically, it's hard to screw up. If you use the default methods and you have an Orbitrap, it should work. So what I did was I set the baseline as MaxQuant, and then I looked at the change in relative to the DDA versus the DIA, and these are the exact same samples run 2 to 3 different ways, right? The gas phase fractionated, the chromatogram, narrow versus wide, and then DDA. And so if you sort by number of peptides, the gas phase fractionated one with the chromatogram library with PanHuman worked the best. And you can go all the way down the list, and what's interesting is it doesn't start to get worse than DDA until you hit all the way down to the wide window searching the FASTA directly, right? Which you would expect. The wider the window searching a FASTA directly, you wouldn't expect it to do as well, and it doesn't. It does about 30% less than DIA. But there's really no reason you would do that. So like if you do the 2x gas phase fractionated library by itself, and you search the FASTA, which would be right here. So you just do a 2x injection, and you search against the FASTA without a chromatogram library at all. You're still about 62% more quantified peptides than DDA, which is nice. And it only starts to get worse once you search wide window with the FASTA. So even all the way down the list is still better than DDA. And these numbers are higher than in Brian's Nature Communications paper, but I'm not really sure why. Like this is 220, so the top performer quantified 233% more than DDA, which is, I think didn't your paper say like 60% or something, Brian? I don't remember.
Yeah, I think that was at the protein level too, though.
Okay, so let's look at the protein level. Okay, so we'll look at the protein level. And so what I set the baseline at is 2 peptides per protein, because Scaffold GA defaults at 2 peptides per protein, which I think is a good default. And you can see how it's about 33% less than 1 peptide per protein, which we all expect, right, with DDA, right? You do 2 proteins per 1, you expect about a 33% drop, and that's what we get. And then you can compare these, and the top performer was the 2x gas phase fractionated with the chromatogram library made against PanHuman. So for 3 samples, this takes 12 runs, but it is about 147% increase over protein level and DDA. So at least I don't know if this is a fluke. This is an N of 1, right? So I have to do this experiment multiple times. I just don't have time. But it doesn't start to get, on the protein level, it doesn't start to get worse than DDA until you get to the wide window of FASTA. So you take the 8 Dalton and search against the FASTA, and then it starts to do worse. But other than that, everything's better. So even the wide window with the chromatogram library made with the wide window, let's see, where's the wide window only? The wide window PanHuman only, so that requires only 3 runs, 8 Daltons apiece. It's still, my numbers are a little high, like 52%. I don't know why I don't think it should be this high, but it turned out to be in this case. But if you do the 2x gas phase fractionated with the PanHuman library only, which only required 6 runs, so no chromatogram library, but still 143% more, and quantified 4,583 proteins. It was a lot. So I was happy with that. And so what's interesting is that if you look at one of the take-homes here, is that it really makes a big difference whether you do the PanHuman or a chromatogram library. So you go from like 4,533 to, let's see, if you don't do it, you just do it first at FASTA, 3,283. So it drops by almost 1,000 proteins, right? And so you may ask yourself, well, why do you want to do that? And you may not have any choice, right? Like we use like a rat sample, and there's no chromatogram there's no public libraries for rat, and so this is kind of what you can expect. So one of the things, and you'll see this with Sue's data too, is that it really works really, really well with human, and the PanHuman library. Like the data is just is astronomical. It's just wonderful. But once you start getting away from human, it's still really good, but it's not as good as human. Like I wish there were these kind of libraries for every organism, right? Because even in building your own chromatogram library, it's not as good. Because like if you build the chromatogram library without the PanHuman, it's not as good, right? It resulted in like half the number of proteins as it did in the first part of the talk. It went from 2,300 to 4,600. Why that is, I don't know. Anyway, and so I plotted the number of MS hours needed by the proteins quantified, and these are all the different methods I tried. And I think the best bang for your buck here, for 3 samples anyway, is a 2x gas phase fractionated PanHuman library without using chromatogram library. So this only required 6 runs, and it then quantified the most number of proteins. So anyway, I think this is a pretty decent method. I think it works okay, I guess. And it only requires 2 injections per run. I think the only other thing you have to look out for is the number of scans across the peak, which I just tried to count by hand, and that's kind of one of the things in my wish list. And so I got this data from Susan Rick before the talk. And so if you look at the missing values, so here's the max quant missing values, and then here's the missing values for the 2x gas phase fractionated. So it's still pretty high. I mean, it's between 8 and 10%. And I just calculated this like while I was sitting back there in the talk. And then you can compare this to TMT, which is much lower, but there's still a good amount of missing values going on with this. And I want to try to do a wide window and see if it's any different. It might be, I don't know. Or maybe it's better. I don't know. Okay, so another example, so this is a good example of human and non-human. Another good example where DIA really shines in the core facility is Serum. So it's like DIA was made for Serum. Like it's made for samples that have highly abundant proteins in them that span a lot of, like Serum or leafy tissue with rubisco or something that's highly contaminated with like 10 proteins. DIA is really good for it. So like at first we did some samples with rat non-depleted serum, and I'm like, well, I don't know, I'll try it, see if it works. And we quantified about 300 proteins, which isn't a lot. I think with human in the PanHuman library, you could probably get up to 600 or 700 or even more. But with rat, we got 300 proteins. I'm like, oh, it isn't very good. And so I sent it back to the people, and they're like, wow, this is awesome. I can't believe you just quantified 300 proteins in our serum. And a lot of these really make sense because there's some rat that had different conditions going on, medical, like biological conditions. A lot of the proteins made sense. And I really thought about this for a long time, and it's like, wow, I thought this data kind of sucked. It was only like 300 proteins. And then I think about it, I'm like, well, it's kind of difficult to quantify 300 proteins in serum. I mean, if you're going to use ELISA or some other way, it's probably going to be a lot more expensive than doing it this way. So this was actually a really useful sample for analysis for these people. So I'm starting to do serum again. So but with DDA, I never attempted serum. There's like maybe five labs in the country that could do serum proteomics and get thousands and thousands and thousands of proteins. And you have to deplete them, and you use these depletion columns, and they suck, and they're really expensive. And so now you can analyze non-depleted serum, and it's actually, the data is very useful for people. And then here's another example where we have a low protein ID example for DIA, where we only quantified about 242 proteins. This was infected grape sap in California. So you can imagine this is a very hot topic in California because of all the wine production. And so there's not a lot of, how many proteins are in grape sap? I don't know, not a lot. And so we identified quantified about 240. And a lot of these are really, this is an infected grape sap example. And this is one protein, this is the infected, and this is the non-infected. And you can actually see proteins that are changing drastically between the infected and non-infected, and this is really useful data. This is data like these people were ecstatic. Like this is stuff that was never known before, and you can imagine even if you have a low ID sample that even quantifying stuff accurately, even if it's only like 200, 300 proteins, can be really important depending on your biological system, right? Okay, but I do have some I know I've gone a little long, but I do have some wish lists for Scaffold DIA. I wish it would calculate the scans across the peak for every peak and then average them. So there's like a new function in Skyline that's supposed to do this, but it didn't work. I tried it. So I tried putting the DIA data into Skyline, because Skyline has that new scans across the peak thing, and it didn't work. So I wish there was something in Scaffold DIA that would do that. I wish there was a raw peptide level export with the raw data, with the intensities without the imputation and the normalization, and you can do stuff yourself. I wish there was a less confusing way to make the chromatogram libraries when one's staggered but your wide windows aren't. The GUI needs to be faster. I don't want percolator to crash. And I would like some more diagnostic plots, like the p-values. I think it's really important to plot your p-values, especially if you're doing multiple testing correction. Like if you go back and read the original Benjamin E. Hochberg, I think it was an R vignette or something. He has a really good summary of it somewhere where he said your p-values should look like this. And if you make a histogram of your p-values, and if they don't, this correction is not going to work. So I think it would be good to plot your p-values. So in conclusion, at least in my lab so far, Scaffold DIA seems to work better than DDA in almost all circumstances. Like, you may need one extra run for a sample, but the data is far better. It's way better than MS1 LFQ in my hands, in my lab. And I think that 2x gas phase fractionated method works okay, I think. I don't know, it seems to work okay. And it seems to even work on older instruments, I think. So we tried this on the Q-Exactive, and it worked okay. And then using public libraries with your chromatogram library works way better than using a FASTA, which I found out thanks to Sue, which doubled the number of proteins quantified. That's not obvious. That's not intuitive, by the way, from the software. I didn't mention this, but DIA runtimes can be shorter than DDA, so it increases the efficiency of your instruments. So like your number of proteins quantified will not drop as dramatically with DIA as they do with DDA. Yeah, and it works okay for undepleted serum. So anyway, we've been really happy with Scaffold DIA. These are the people in the core that make all this happen. Michelle and Tony and Justin and Danielle. We do have a short course every summer. We do teach, we're going to teach Scaffold DIA this year. So if you're in the Bay Area and you want to come by, you can sign up. We do have people from all over the world, so it's kind of a neat. I wish we had 2 weeks to teach it. It's not going to be a long, but we are going to teach Scaffold DIA. So. Anyway, that's it. Sorry, I went a little over. If you guys have any questions, the data, there's a lot of data in these slides. So like you totally could have this talk, or they'll get it from somebody. I can even give you the Scaffold DIA files when I have time, when I organize them. So anyway, that's it. If you guys have any questions, or I think I kind of ran over, so if you guys wanted me to do it after, you guys can ask me, or if you don't have any questions.
That was good, yeah, sure. So on Thursday, just to plug, I have a poster about how to make synthetic libraries that work as well as
right with the ProZip, right? Yeah. So did you see that tweet that Mike, when I was talking to Mike about this on Twitter?
I didn't see it though.
So that's what I was talking. I posted this question on Twitter, and I was like, well, this sounds great. Why do I have to make chromatogram libraries anymore?
So the issue is you still have to make chromatogram libraries to make it work.
Yeah, why is that?
And it's because the data quality of ProZip is good, but it's not that low.
Okay.
So you need an intermediate.
Okay. Now there's another way to do it too. So is that going to be built in the Scaffold DA eventually, or how do you?
There's a workflow that you can start taking.
Okay. Because we tried to download the ProZip software and we couldn't get the NVIDIA. That's a complicated install to get it working with.
It's very hard.
Yeah. Anyway, so I think the take home is that at least for our facility, if you want to run less than 6 samples, I think just doing 2 injections work pretty well in our hand, and it doesn't.
I haven't tried it yet. You sent me the files, but I haven't had a chance.
I think it works okay. I wish there was a different way. I wish there was a better way to count the scans across the peak, so I can verify that there may be enough or maybe not enough.
So you can do that actually as a query into the program. So there's a custom export that you could do to actually get that number.
Okay, cool. So I can go back and try it.
So one more time, you got more proteins when you search the Spectral library than with the chromatographic library, or the other way around?
Well, so I did a lot of permutations, and it's kind of complicated. So
I think the fractionations are always give you more.
it did, because it did.
1,000 more, that's what you said?
It did.
Than the PanHuman?
It did. Yes.
So we are still, so those like me who are doing the immunopeptidome, so a human immunopeptidome display, so we really have to do the chromatography to the.
Oh, I don't know. I don't know if I really understand this data.
You should.
Because, Brian, do you understand it? Like,
So what about it?
so like this is the traditional 8 Dalton wide window made against the narrow chromatogram library. You want me to sort by peptides or let's sort by peptides? So like that's this one here. So this is the wide window, and then the narrow chromatogram library made with PanHuman, and it quantified 3,800, 100, about 3,000,
Yeah, and so
3,800.
Brett, if you do 2 acquisitions, it's always going to be better than if you did 1, right?
Well, this was actually 9 versus 12 for 3.
Sure,
Yeah.
in total,
Yeah.
yes. But the data that you're making your measurements off of, your quantitative measurements, it's really just 1 acquisition.
Right, the
Right.
wide, right.
And so it's 2 acquisitions when you're doing a 2x gas
But
phase
it-
fractionation?
Yes, but it's gas phase fractionated.
Yes.
Yes, so it's like the chromatogram library, but only 2 runs covering the entire.
Yeah, so if you've got less than 6 samples, the 2x strategy is a great strategy.
But what if you have 20?
But if you have 20, then the 1x strategy is
Number
overall
1.
better, right?
Yeah. Well,
Because
it's the only option, I would say.
Yeah, and I forgot where Scaffold DA crashes. It was percolator, but I forgot what would cause it. I think it would run out of memory or something.
No, I think that you run against FOSTA is running out of memory, but if you
That
use
does that too.
Spectral Accounting,
Yes,
it's okay.
that's right. Right, when you search
Yeah,
against
you can't-
FASTA.
I use
That's right.
many samples in with DDA Spectral Accounting, works very well.
Yeah.
Yeah, you can't search more than a few.
So that's the one thing I didn't do DDA spectral libraries in this analysis. So that's, well, except the PanHuman is DDA, right, Brian?
Yeah, it
But
is.
I didn't make my own DDA spectral library. Anyway, that's how we use it in the core. I've been really excited about it.
Yeah, cool.
Thanks very much.